So in the previous lesson, you formulated the multiple linear regression problem as one of minimizing the residual. So in this lesson, let's see how to calculate that minimum. Now to do that, you'll need the vector analog of taking the first derivative. So that mathematical tool is something called the gradient. So let's start by seeing how it works and then apply it. So let's suppose you have a vector variable, theta, and let's say that it has n components, theta 0 through theta n minus 1. Now let's further suppose you're given some scalar function of theta. Let's call it g of theta. So that means g produces a scalar, or a single as opposed to a vector value. For instance, let's say theta is the vector of length 2, and let's say g of theta is the 2 norm of theta squared. This right-hand side is just a single number, or scalar. Indeed, from the definition of the 2 norm, g is theta transpose times theta. In this case, that's theta 0 squared plus theta 1 squared. Next, let's define the gradient of g with respect to theta. We'll denote it by the nabla, or upside-down triangle, sub theta applied to g. And let's define it to be a vector. Each element of this vector is a partial derivative of g with respect to some element of theta. So let's revisit our previous example. There, theta was 2-dimensional, and g of theta was theta 0 squared plus theta 1 squared. So what's the gradient? Well, it's a vector of length 2. Its 2 components are the partial derivatives of g with respect to theta 0 and theta 1, respectively. So let's substitute g, and then evaluate the derivatives. That gives you 2 times theta 0 as the first component, and 2 times theta 1 as the second. Simplifying, that's just 2 times theta. Now that's very abstract, so let's look at an example visually with the help of a Jupyter notebook. Let's start with the same example, here using the variable x instead of theta. The code just implements the formula. Now let's create a grid of x0, x1 points. Here's what the outputs might look like. Notice that capital X1 is the transpose of capital X0. Now let's apply the function f to all of the points on the grid. Let's draw the results in 2 ways. First, as a 3-dimensional surface, and secondly, as a 2-dimensional contour plot. Since we're squaring each component, we basically get a paraboloid, the multidimensional analog of a parabola. The left shows it in 3D, and the right shows the same thing, but as a flat contour plot whose minimum value lies at the center. Next, recall the gradient calculation, which we can implement as a Python function. When we evaluate it, we will get vectors at every point instead of scalars. Now let's add these to the contour plot as little arrows at every point. The arrow will point in the direction of the gradient and will be scaled proportionally to its magnitude. Here's the result. Notice how the arrows point radially outward away from the minimum value. They also increase in length as the paraboloid gets steeper. I hope this picture builds your intuition for what the gradient does. In particular, it points in the direction of steepest ascent. But that's not all. Do I sound like a salesperson yet? The gradient is also 0 at extreme points. So that's the same thing as what happens to the 1-dimensional derivative. You now have all the building blocks you need to solve the multiple regression problem. Remember, that's to find the theta that minimizes the squared 2 norm of the residual. Now, rather than me showing you in detail how to do it, let me give you the facts that you need to do it on your own. And as an exercise, you should derive these facts and apply them to obtain the final result, which I'm about to show you. The first is just the definition of g of theta. Here's the second. Suppose v and w are two vectors. Then the gradient of v transpose w with respect to v equals w. An easy way to remember this one is to recall its scalar analog. The derivative of x times a with respect to x is just a. Here's a third factoid. The gradient of v transpose v with respect to v is 2 times v. Can you think of a scalar analog to help you remember this one? Now here's the fourth and final fact. Suppose capital M is a matrix. Then the gradient of v transpose times m times v is equal to m plus m transpose times v. Armed with these facts, you can show the following. First, the gradient of g is 2 times x transpose x theta minus 2 times x transpose y. You can then ask, what is the value of theta, let's call it theta star, at which the gradient is 0? After all, that would be an extreme point and therefore a candidate for minimizing g. And that theta star must be the solution to this equation. X transpose x times theta star equals x transpose y. This system is sometimes referred to as the normal equation, or sometimes the normal equations, plural, depending on your point of view. Now let me suggest one final exercise. Remember the case of a single predictor, or n equals 1. In this case, the data matrix, capital X, is just a single column of predictor values for each observation, along with one extra column of ones. Now remember that this extra column allows our linear model to have an intercept term. Using u to denote this column of ones, capital X has two columns, little x for the predictor and u for the column of ones. In addition, theta is the two-component vector consisting of theta 0 and theta 1. So from this starting point, plug capital X and theta into the normal equation and determine theta star. Then ask yourself, how does that compare to the result we got from the other lesson where we analyzed the single predictor problem? So to summarize, this lesson was about building foundations, using the gradient for solving the multiple linear regression problem. And because it's based almost entirely on linear algebra, it should, at least in principle, lead to a compact and efficient solution. Now, there's still one big detail, which is how exactly do you solve the normal equation? So to help you through that process, we've put together a couple notebooks. So at this point, you should pause, take a moment to review everything that we just covered, and with that as background, you should be able to go through the notebooks and get a working numerical algorithm for the multiple linear regression problem. Good luck.